I'm going to introduce material on electrochemistry, which will be covered on the very last exam of the semester during the finals week. Let me put that up here. Electrochemistry. In your book in Brown, this chapter 20. So I want to get this material presented, and since we don't have any more time left after this to get in a review, I'm going to immediately start the review after the introduction of the material. So let me share the PowerPoints here. There we go. Now let's make a slideshow. There we go. All right, electrochemistry. By now we know what chemistry is. The electro part of the name simply means that we're studying the transformation of chemical energy into electrical energy. Think things like batteries or generators, alternators. On a larger scale, dynamos, except that they're converting most of them are converting physical energy into electrical energy, but some chemical energy. For instance, coal-fired power plants will take coal and burn it, boil water, create steam, run that steam through a turbine, and power the dynamo. So we're going to look at the very basics of what's going on. And actually, we're not going to go through the problem of converting chemical energy into some sort of physical change so that we can get power from it. We're going to go straight from the chemical reaction to the electrical power. So in that respect, think batteries. All right, here's a review. This is just to reintroduce some terminology. And to do that, we'll go back to the mnemonic device. Remember this one? Right? Oxidation is loss. And what we mean by there is loss of electrons. Reduction is gain. Oops. Mean that. So once we've defined these terms, then it's important to remember that oxidation and reduction processes in chemistry always occur together. If something is oxidized, something else must be reduced. Those electrons that one item loses have to show up in a reduction. So when we write a balanced chemical equation, and if we identify it as an oxidation reduction process or redox reaction, that we have to account for all the electrons that are moving, and the number of electrons in that balanced equation that are lost by something must be gained by something else. And in that respect, let me go to the, let's see, there's the oil rig. Okay, let's say we have, let's just make it generic. And let's get another marker. So we're going from A plus B to C plus D. Let's say A loses electrons. And it becomes C. So let's say we have a loss of electrons. Then this one must gain electrons. All right, so these electrons are transferred to this one in order to produce these products. This one is said to be oxidized. This one is said to be reduced. Okay. We also have another term. It's called reducing agent. So if this one is oxidized, it is the reducing agent. In other words, this one, the oxidation of this atom or molecule is responsible for reducing this one. So if this one is reduced, then it also must be an oxidizing agent. Okay, terminology. Okay, in order to determine how the electrons move, we need a bookkeeping scheme, keeping track of the electrons. Where do they start? Where do they end up? Now, this is going to have the appearance of being a charge on various atoms, but that's not the intent of oxidation states. Oxidation states simply is a bookkeeping scheme, and it looks like charge, but it's not necessarily charge. It may be, and that should become obvious when we go through the rules. All right, so first rule. If the atom in a reaction is by itself, it's an element, then its oxidation state is 0. For instance, if we have hydrogen gas and oxygen gas, they come together and they make water. Right? So we need 2 here and 2 here. The oxidation state assigned to this element is 0, and to this element is 0. Right? That's the easiest rule. If we have some ions involved, then monatomic ions, there's only one atom and it's got a charge, then the oxidation state on that atom, that element, is the charge. Let's see. I don't know, if we had sodium as a reactant, then its oxidation state would be +1. In covalent compounds, we assign an oxidation state for oxygen of a -2. So this would be, it's part of a covalent compound, it's a -2. The only time that does not hold is if that oxygen is part of a peroxide. And a peroxide is any compound that has covalently bound oxygen, and then on either side has some other groups. Doesn't matter what they are. This one right here, that peroxide functional group is 2-, so each one has to be 1- each. That's the only exception to oxygen. All right, what's next? Hydrogen. If hydrogen is in a covalent compound, that is, it's paired with a non-metal like water, then hydrogen is a +1. Okay? If, on the other hand, hydrogen is paired with a metal, our example there is aluminum hydride, right? Then the hydrogen must be a -1. And the reason for that is metals are much more likely to give up electrons. They're much more likely to be oxidized. So hydrogen has to accept those electrons. So aluminum, we know from our nomenclature days, aluminum tends to be a 3+ charge. So it needs 3 of these minuses to balance that charge. And that should be one of our next rules, actually. We got to do fluorine first. Fluorine in any compound is always -1. All right. For a neutral compound, and it doesn't matter if it's ionic or covalent or anything in between, the sum of the oxidation states must be 0. So for this water, that's what we have here. For that water molecule, we have a two minuses here, and we have a 2 times 1 plus is there. That balances to 0. If, on the other hand, we have a polyatomic ion, such as sulfate, right? It has a charge. So the sum of these oxidation states must be the charge. Right? So that oxygen is a -2 times 4 of them means we have 8 minuses for the oxygen. But we don't need to neutralize all of them. We just need to balance 6 of those, because we need to keep 2 of those minuses out for that charge. So these 6 minuses have to be balanced by a 6+ on that sulfur. And you can check yourself. 6+ and 8 minus equals 2 minuses. All right. Got any more rules? Yep. Alkali metals. First column in the periodic table. They are always assigned an oxidation state of +1. Their next door neighbors, the alkaline earths, they're always assigned an oxidation state of +2. When we get to other elements, especially the nonmetals, when we're assigning oxidation states, we have to make a choice. And our examples here are like PCl5. Right? Where do you start? Right? We haven't said anything about what's the oxidation state of chlorine. But if you've got a situation like that, then you look to the one that's the more electronegative. And that one is the one you fix. Since this is a halogen, it's to the right of phosphorates, it's more electronegative, we assign an oxidation state of -1. That means we have 5 minuses here. That means this one has to be a 5+. Right? Like I said before, this is an oxidation state. Excuse me. This is a bookkeeping scheme. It's not necessarily that these have those charges. It's just a way for us to track the electrons. For the other example they have there is cyanide. Right? Okay, so nitrogen is to the right of carbon. So we assign the oxidation state to nitrogen based upon its position in the periodic table. Remember, halogens are -1, then chalcogens are -2, pnictogens, well, nitrogen in this case, is a -3. So we say, okay, this nitrogen is -3, but we need to hold one of them out. So we only balance a -2. That carbon is a +2. All right, so here's some examples. Let's see if we can assign oxidation numbers for the elements in these compounds using the rules that we've learned. So potassium dichromate. Let's start over here. Right? We know that the alkali metals are +1. That means we have a total of +2 here. We know that the oxygens are assigned a -2. So that's a -14. Okay. Now we put those together, we get a -12. That's the charge that needs to be balanced by the chromium. And we have 2 chromiums. So each one of them must be a +6 to give us a +12 and balance the charge for that compound. All right. How about this polyatomic ion? Right. That's the carbonate. Oxygen is a -2 times 3 is a -6, but we need to hold 2 negatives out for the charge. So we really only need to balance a -4. That makes carbon a +4. Okay. How about this one? MnO2. -2 for that oxygen, -4 total. It's a neutral compound, so this manganese has to be a +4. Okay. We did PCl5 already, so I'm not going to do that one again. SF4. Right? We said fluorines are always -1. So that's a -4. This one has to be a +4. Sulfur must be +4 to balance. There we go. Okay. Now that we know how to assign oxidation states, then we're going to use them in as our bookkeeping scheme to track which species are oxidized and which are reduced. When we do that, there's a purpose. We need to balance equations, and redox equations are not always, but often difficult to balance if you simply use the budgeting scheme that I taught the class in the first semester. All right. So what we use a method called half reactions, and we call them half reactions because one of the reactions is oxidation step and the other is the reduction step. There's half and half, and you balance those two and then you bring them back together for the final balanced equation. Sometimes that's very often, actually, it's necessary because you'll notice that we've got protons in here and water molecules in here, and really the oxidation reduction business that's taking place is with the manganese and the iron. So how did we get the waters and the hydrogens in there? Well, that's part of the procedure. Okay, and you may not be given those hydrogens and waters if you try to use the simple budgeting method. They may not be there. But since these reactions occur in aqueous solution, and we know that water very often is a reactant or a product of oxidation reduction reactions, then we have to be sure and include them in our balancing scheme. So here's the way it goes. This particular reaction, you'll notice that we've got ions, 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 and this is the only neutral molecule in the bunch. So what you'll see with redox problems is that you may only be given the relevant species that are going to be oxidized and reduced. And the counterbalancing ions For the manganate ion, there might be some cation there that balances it when you put it in solution, like a sodium or a potassium or something like that. Or the iron might be coupled with, say, nitrate or chloride. But the business of oxidation reduction only takes place for these ions. So the charges may not necessarily balance. But this equation, we're told, is balanced by the oxidation, the half reaction method. And if we break it apart into its two half reactions, then it would look like that. Let me see. Let me get my hard copy so I can follow along. Yeah. Okay. I'm going to take this reaction right here, and I'm going to present it to you the way you would see it on a review document or on an exam. You would be given something like this. Let's see, MnO4 minus, and then that would be reacted with 2 plus, and it would yield Mn2 plus and Fe3 plus. Okay. What we have to decide is which ones of these are reduction and which are oxidation. And the best way to do that is to get your oxidation states in line first. So for manganese, well, for this one and that one and that one, they're all just the charges. That's it. All right, so those are already given. This one, we have a -2 times 4 is -8. We need to hold one out, right? And that will make this a +7. Okay? So what's happening to the manganese? The manganese is gaining electrons. It is being reduced. Right? So it gained 5 electrons per manganese. The iron, on the other hand, is being oxidized. It has lost 1 electron per iron. Right? Excuse me. And we know that that's not balanced. For one reason, 1 electron doesn't balance 5 electrons. Okay? So now that we know which one is which, we can put them in separate half reactions. Let's do it over here where we got more room. So the reduction step would be the gain of electrons. So MC. Let me move this one. Oh, that should work. MnO4 minus. And then that's going to give us Mn2 plus. This is reduction. And oxidation would be the iron. 2 plus, the iron 3 plus. Notice I'm leaving a lot of space in here for the next steps. Okay, now that we know which is which, first thing we do is make sure that the elements are balanced. Those elements that are not hydrogen and not oxygen, be sure they're balanced. 1 manganese, 1 manganese, 1 iron, 1 iron. We're good there already. Then you balance the oxygens with water. So if you got 4 oxygens on this side, you need 4 oxygens on this side. And those oxygens show up as water. But now what have we done? We've added 8 hydrogens. So 8 hydrogens have to go over here. Right? So 8 hydrogens and 4 oxygens make 8 hydrogens and 4 oxygens. Right? So that's balanced with hydrogens and oxygens. How about here? We don't have any oxygens, so we don't have to worry about it. No oxygens, no hydrogens here. Next thing you do is you balance electrons. So if this is reduced, that means we have added 5 electrons on this side, right? These 5 electrons are added to that manganese to give you this manganese. And this is oxidation step. We lost 1 electron, so that electron is a product. Now we need to balance the electrons. We have 5 here, only 1 there. So we have to multiply the entire reaction through by 5. All right, so that makes 5 there, 5 there, 5 there. Now we can add them back together. Kind of like Hess's law. These 5 electrons are going to cancel. 5 on that side, 5 on this side. They cancel one another. And now we have MnO4 minus plus 5Fe2 plus 8 hydrogens, actually 8 protons. This is an acidic solution. Okay. 1, 2, 3, 1, 2, 3. Then we have this manganese and this number of irons and 4 waters. Right? Then you see if you can reduce it any further. Right? Can we divide through by anything and make it simpler? No. That's 1, 5, 8, 1, 5, 4. That's as simple as it gets. And that's the reaction you see there, balanced. And these are the half reactions and where they came from. Okay. These are steps in green letters to show you what I just did. Okay. And there's a schematic. The method I used here is for solutions that we know are acidic. They have these protons. All right. Now we're going to learn how to balance basic solutions in a few minutes. Okay, there's another one. All right. First of all, is this a redox reaction? Right. What about that chromium dichromate? Right. What's the oxidation state on chromium? Well, let's see. -2 times 7 is -14. Hold 2 out, -12. This needs to be +12, but there are 2 of them, so that's +6. So that chromium on the reactant side is +6. Chromium on the product side is +3. So we know this is a redox reaction. And then we're going to add sulfite. Right? -2 times 3 is -6. Hold 2 out, -4. This is a +4. All right. Then we have chromium 3+ and sulfate. So this is a -2, -8 total. Hold 2 out. This is a +6. So where's the reduction reaction? +6 to +3. we had to gain 3 electrons. That's reduction. Oxidation, +4 to +6. Lost 2 electrons. Okay? So there are 2 reactions. This one is the reduction. This one is the oxidation. Right? This one is going ahead and using the electrons first, which is fine. I mean, that works because hydrogens and water are not involved in the oxidation reduction step anyway, so we can add them later. So you can do that in either order that's convenient. Then we need to balance. Well, first we had to check to be sure. Oh, they haven't done that yet. Balance the chromiums, right? That's going to need 2, right? I guess we're going to do that one in a minute. Then we're going to balance the, yes, here we go. There's the 2 chromiums. So we're balancing that part. And then we want to be sure that the electrons are correct. So that's 3 times this one to give you 6 electrons to balance those 6 electrons, right? Then we can add them together, and there's our final balanced equation using the half reaction method for acid solutions. Okay, here's another one. Let's see. Oh, they're not going to do this one for us. So we have to do this one ourselves. All right, so which one? Let's see. Let's put it up here. Br minus MnO4 minus yields Br2 and Mn2 2+. Okay, so we know this one is 0. We know this one is -1. We know this one is +2. How about this one? We did this one before, so we'll do it again. -2 times 8, -8, -7, because we hold 1 out for that minus. This is a +7. So the manganese has been reduced from +7 to +2. So the reduction step is MnO4 minus yields Mn2+. And the oxidation step then must be Br minus yields Br2. Okay. Next, we got 1 manganese, 1 manganese, 1 bromine, 2 bromines. There we go. Now we have 2 bromines. Then we go for the oxygens, right? 4 oxygens there. I need 4 oxygens here, which means 8 hydrogens on this side. Okay. Now, how many electrons were transferred? Right? This one went from +7 to +2. 5 electrons were added. Okay. How about this one? -1 to 0. Lost 1 electron per bromine, but there are 2 of them. So that means we have 2 electrons lost. Okay. Now we need to balance the electrons. So how do you balance a 5 against a 2? Cross multiply. So that 2 is a multiplier here. And that 5 is a multiplier here. All right. So that means we got a 2 here. We got a 16 here. And we got a 10 here. We got a 2 there. And we got an 8 here. Okay. How about down here? All right. That makes this one 10. 5 times this one. And 5 times this one. There we go. So now that 10 balances this 10. And we add the rest of them together. So we have 2 MnO4 minus plus 10 Br minus plus 16 H plus yields 2 Mn 2 plus 5 Br2 plus 8 water. So that's our balanced equation, and let's see. No, can't reduce it any further. You can't divide by a whole number and reduce the coefficients any further. That's the simplest. And there it is. All right. That's how it's done. Now, how about the basic solution? The basic solution, I use what I call a fake acid method. You balance it as if it were acid first. Then you change it to basic. How do you do that? Well, let's use this one for example. If we wanted to put this in basic solution, then we would have to neutralize those hydrogens. With what? With hydroxyls. So we would need 16 hydroxyls here, but they have to be the same on both sides. So we say plus 16 hydroxyls there. Okay? What would that make over here? Well, that would make 16 waters, correct? OH minus and H plus always makes water. 16 of them. But notice we got 8 waters over here. So those waters would cancel, and that would leave us with 8 waters over here. Okay? So now we would have 2 manganetes, 10 bromides, 8 waters, 2 manganese 2 plus, 5 bromine, and 16 hydroxyls. That would be in basic solution. And that's it. You just balance it as an acid first and then change it. All right. And there's a schematic for it. Notice that the transition from acid to base is in green. Everything else above that is exactly the same as the acid method. Okay. So if it hasn't occurred to you already, why don't we just balance it for a basic solution from the beginning? Well, how would you do that? Right? That's one question. If you added oxygens on one side as hydroxyls to balance the oxygens, say MnO4, like this. If you needed to put oxygens on this side, instead of water, use hydroxyls. So let's say, what do we have? Maybe 2 here? I think that was it. So we have 8 oxygens, right? So we need 8 hydroxyls. Okay, let's see. That was 7. This is 2 plus, I believe. We're not worried about that right now. We're looking at the oxygens. Okay, so if you do this, that means you need 8 hydrogens on that side. So what form do they take? I mean, what can we do? Just do that? I guess. Then we got to get rid of those acids, though. So we need to add more hydroxyls, don't we? All right, that makes water. But we got to put 8 hydroxyls over here, too. So that makes 16 hydroxyls. I guess that could work. But I don't think it's quite as reliable as the fake acid method. That's why I stick with the acids. It goes much more smoothly if we use acid first and then convert it. Okay, what do we have here? Another example. Cyanide plus MnO4 minus yields CnO minus and MnO2. Balance that one in basic solution. All right, in the interest of time, I'm going to let you do that one. No, I better do that one. I think I remember complexities here. So let me do this one so we can eliminate any problems. Cn minus. So let's get rid of the answer for now. Cn minus plus MnO4 minus yields CnO minus plus MnO2. Okay. This one is 2 minus 2 times 2 is minus 4, so this one has to be a plus 4. And this one, I think we said it's plus 7, didn't we? Yeah. Okay, so this is the reduction step from here to here. So the question is, how do we deal with these two? Well, remember, nitrogen is going to be -3, but we only need to hold 2 out for carbon. This one's oxygen's always a -2. Well, what about nitrogen? Right? We have to make an assumption. It's -3. So -3 and -2 is -5, but we hold 1 out for that minus. That makes this one +4. That fits our scenario. I mean, we know that manganese is going to be reduced, so carbon has to be oxidized. So the reduction step so the reduction step is going to be MnO4 minus, and it's going to yield MnO2. And the oxidation step is going to be Cn minus, and it yields CnO minus. Okay. Now, manganese, manganese, 1, 1, carbon, carbon, nitrogen, nitrogen. Then we go to the oxygens. All right, so we have 4 oxygens here, but we already got 2 here, so we only need 2 more. But now we've got 4 hydrogens. There we go. Okay, we got 1 oxygen here, so we need an oxygen on this side. Now we need 2 hydrogens to balance these 2. Okay, now we do the electrons. Reduction step. Manganese went from +7 to +4. So that's +3. We had to add 3 electrons. Cyanide went from +2 to +4 on the carbon. So that's a loss of 2 electrons. Okay. Now we've got an odd and an even. We have to cross multiply. So 2 times this one would give you 2 here, 8 there, 6 there, 2 here, and 4 there. And then 3 times this one would give you 3 here, 3 there, 3 there, 6 there, and 6 here. So 6 electrons on both sides are balanced. And we can add things back together. I'm going to add them over here. Hey. I'm into electrochemistry. Nobody came to class today, so I just went ahead and started on the next chapter.
Oh, okay.
Which might be good. It'll give me time. Once we finish this, it'll give me time to work some problems. All right, so I'm into balancing equations using half reactions. And we started off by balancing the half reactions in acidic solution. And what I mean by half reaction is we take this equation and we break it up into two separate reactions, one for the reduction step and one for the oxidation step. Reduction is gaining electrons, oxidation is losing electrons. So for the reduction step, this manganese, and we went through some rules for how to determine the oxidation state for each of the elements. You'll have to go back and review that. Now I've gone through this reduction step and this oxidation step, and what I'm doing now is bringing them back together. Now that we got the electrons balanced, whenever you reduce by so many electrons, you must also oxidize by the same number of electrons. So that has to be balanced first, and then we can add them back together. So I've got two MnO4s. And then, let's see, 8 H plus. Right. And then I've got 3 CNs and 3 waters. And that yields, excuse me. Let's see, I'm gonna have to erase these to give me room. We got this side of the equations done. So I just need to bring in this side. 2MnO2 plus 4 water. And then 3 CNO minus plus 6 hydrogens. And that's everything on this side. Oops. Now we need to eliminate things that are on both sides. Hydrogens. We got 6 on this side and 8 on this side, so now this one is 2. We got 3 waters here and 4 waters here, so that one goes out, and that leaves us with 1 water on this side. Now, at this point, we're balanced for acidic solution because you got those protons. The next step changes this into a basic solution, and we do that by neutralizing the hydrogen ions. So I need to add 2 hydroxyls here and 2 hydroxyls here. Right, so this turns these into 2 waters. Right, hydrogen ions, hydroxyls always make water. So now we got those 2 waters here, and we got a water over here. So now this water goes out, and that leaves us with only 1 water here. So the balanced equation for basic solution is 2MnO4 minus plus a water plus 3 CN minuses yields 2MnO2 plus 3 CNO minus plus 2 hydroxyls. And that should be the next animation. There it is. Mine are not in the same order as theirs. Okay. Now, as I mentioned earlier, electrochemistry is the study of conversion of chemical energy into electrical energy. And the simplest way to do that is with a galvanic cell, otherwise known as a battery. This was named after an Italian who produced the first battery. He just stacked zinc and copper like that, just stacked them up, pure zinc and pure copper. And then between them, he had acid soaked material of some kind. I don't know, linen maybe. And then he had an electrode here and electrode here, and he found that when he brought them close together, you got a spark. So that was the first battery. All right, so for our purposes though, the galvanic cell, while it does actually convert chemical energy directly into electrical energy, when we consider oxidation reduction reactions in terms of half reactions, then it becomes clear that we need to, if we want access to those moving electrons that we've identified in that complete reaction, we need to provide an external route for those electrons to move. Right? If we just put the two solutions together, the electrons will move and the reactions will occur, but we won't have access to any of that energy of those electrons moving from one to the other. So what we have to do is separate those two half reactions such that the electrons can only travel through an external circuit, and then we can tap that energy. That's the idea behind the two half cells in a galvanic cell. Now the process, of course, in order for it to produce energy, must be spontaneous, right? And we've looked at spontaneity in terms of free energy and entropy. And we're going to tie those together in a few minutes. But the reaction must be spontaneous in order for us to get derive energy from it. The other factor is if we've got two half reactions, say in these two vessels, and let's say they're in solution. How about that? And we have an electrode here, an electrode here. We need something to conduct the electrons, and then we bring that through an external circuit and maybe put a meter on it so we can measure the movement of electrons. The reactions that we've identified as reduction and oxidation occur at the electrode. It really makes sense, because if the reactions occur over here, where do the electrons go? They go wherever they want to. They have to occur at the electrode in order for the electrode to pick up the electrons and send them across. So here's an example. The thing that's missing here is the fact that electricity only moves in a circuit. In other words, it moves in a circle. That's what circuit means. It goes from one place to the other and back around. So if there's a broken circuit, right, you've got reaction here and reaction here, but they're not connected, there's no way to move those electrons. So what we have to do is bridge the gap. This is one way to do it, with a salt bridge. It can be virtually any salt as long as it's soluble. Commonly used salts are potassium chloride. It works. Or sometimes you want cations and anions here that are common to the other solutions. The other way to do it is put a salt bridge between them. A porous disc between them. Then you can complete the circuit that way. The advantage to a porous disc is there's less internal resistance to the movement of electrons. With this, all this space in here that's occupied by your salt, usually it's either got a plug at the end to keep direct mixing from happening, just let the ions move, or it's filled with auger, right, a stiffening agent, so that it won't move. And that adds resistance to the movement of charges. All right, so if you're expecting a volt here, a certain voltage up here, it's going to be less because of this internal resistance. And that's not the only place that internal resistance occurs. It occurs all through the system. Every battery has internal resistance that reduces its effective voltage. Okay, this is a galvanic cell. Let's see. Right, there's a salt bridge, there's a porous disk. By convention, we always have the oxidation step on this side, on the left-hand side, and the reduction step on the right-hand side. So, which way do the electrons move? Well, for the oxidation step, you have to lose electrons. So the electrons enter the electrode and travel this direction. Then when they get over here, they're added into the reduction step, and they add to something on this side. Well, if these electrons are moving here, you're losing negative charge here, right? And producing positive charges over here, right? To balance that, the salt bridge introduces negative charges on that side and positive charges on this side to keep the static charge neutral. Okay. Oh, by the way, let's see, there's some more animation here. Right. The oxidation is called the anode. This side is the anode. And the reduction side is called the cathode. Just memorize it. I can't give you a good explanation for it. All right. So what do we mean by cell potential? That's another way of saying voltage. How much push is there behind those electrons to get them from one side to the other? The higher the voltage, the higher the push. But that's a qualitative expression. We can actually quantify that push. Now, sometimes it's referred to as a pull, cell potential as a pull, but I prefer driving force as a push, electromotive force in the cell. How strong is the push for those electrons to go over there? And we can measure it in our external circuit. The unit, of course, is the volt, right? And the volt means 1 joule of work for each coulomb of charge transferred. So 1 volt equals 1 joule of work for every coulomb of charge transferred. Now, we haven't defined what a coulomb is yet. It's a holdover from the early days of 1700s, thereabouts. But we do have an equivalence for coulomb. What's a coulomb of electrons in terms of moles of electrons? We do have a conversion factor, so don't worry about that, because we need to know that. If we're going to do stoichiometry with a balanced equation and we know the electrons are moving and how many electrons, then we need to be able to convert that to coulombs in order to use this. It's a bridge. This unit conversion is a bridge between the chemical and the physical. But it takes that much work for a certain amount of charge. Right? If we get more work involved, then the voltage goes up. All right. Oh, I got a video. Maybe this will help explain it a little better.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. Cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching a cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
Okay, there was a mention there. Oops, sorry. There was a mention there of metal activity. We're not going to go into that in any great detail. It just means that in terms of relative ionization energies, it takes less energy to release electrons from zinc than it does from copper. So the zinc tends to be the one to lose electrons or to become oxidized, and copper tends to be the one that is reduced when they're in the same vicinity. And the point was made that on this side, we're taking copper 2+ ions and adding 2 electrons, and they're being plated on that electrode as copper metal, right? We have reduced that copper 2+ to a copper 0, and on this electrode, that's where it's plated. So the mass of that electrode is going up as the reaction proceeds. And over here, the zinc is becoming zinc 2+ plus 2 electrons, and the electrons are moving over like that. So we're losing zinc from that electrode, and the mass of the zinc electrode is decreasing over time, and you can measure it. All right. How do we measure this potential? Like, we put a meter up here and measure the voltage. You know, what kind of force is being applied to push those electrons? Well, there are 2 ways to do it. We can use a voltmeter, and a voltmeter is very cheap to make. All you need is a standard, excuse me, yeah, you need a standard resistor, and we use Ohm's law. I don't know if you've never had physics, you don't know what Ohm's law is. R is resistance, and actually the way Ohm's wrote it, it was resistance equals voltage per current, and current is in an amperage, in amps. So volts per amp is resistance. That just means for any resistor, how much push does it take to get a certain amount of current through that conductor in a given amount of time, because an amp equals 1 coulomb per second. So if you know the value of the resistor, which is given in ohms, use the Greek omega. It's given in ohms. If you know exactly how much that is, then when you attach it to the electrodes and it tries to push past that resistance, then your circuitry measures the current that's allowed to pass and converts it into a voltage. The problem with voltmeters, let's see. Yeah. The problem with voltmeters is this is not a reversible process. So the maximum cell potential means that you cannot ascertain the maximum cell potential cannot be determined as long as there is current moving. It has to be zero current moving in order to measure the maximum voltage. So this is really an estimate. Some meters will make corrections, add a correction factor for the size, the amount of current you have, and those, of course, would be more expensive. But there's a better way to determine the maximum cell potential, and that's using a potentiometer. A potentiometer gives you similar voltage. It gives you values that are similar, like volts. But what a potentiometer does is it takes a circuit. Let's see. If we have a potentiometer here, it applies a known voltage, a calibrated voltage in reverse. Right? So this is the voltage of the potentiometer. This is the voltage of the circuit. And it has to be very finely calibrated to give you a known voltage. And as you increase the voltage, you watch the current, the movement of electrons. And once the current stops moving, it comes to zero, then you look at the dial that says voltage, and it'll give you the voltage that's required to stop the electrons from moving. That's why potentiometers are much, much more accurate and much more expensive. And they have to be regularly calibrated for that known voltage. Okay, those are the two ways. Voltmeters, actually, when you go to the store and buy one, you're not going to get a voltmeter. You're usually going to get a multimeter, which will do several things. But voltmeters are a lot cheaper, and they serve our purpose. Okay, there's a digital voltmeter, and it measures the potential for that cell. Now, you can measure the cell, you can build a cell, a galvanic cell, and measure the voltage, right? Or if you want to, like when we were using thermochemistry and Hess's law, we could set up a reaction that we wanted to investigate and test it beforehand to see how much heat would be either added or delivered, endothermic or exothermic, from that reaction, so that we could see, is it going to be safe, for instance. Well, you can do a similar thing with galvanic cells by using standard reduction potentials. And you can assess the maximum voltage that should be available from any galvanic cell that you want to build. And of course, expecting that it'll be less than that because of other factors. So let me explain what the reduction potential means. when you go to a reference table, and there's one in your textbook, and there's one here that I've extracted from my textbook and put in these slides. The standard reduction potential is not something that you do independently. You cannot take a species like a metal or anything else and reduce it on its own. You've got to have something to compare it to, because remember, oxidation and reduction always occur together. So if you're assigning reduction values to this half reaction, it has to be paired with something else. And that something else is the standard hydrogen electrode. Okay. And when we have that little 0 up here, that means the values are reported for standard conditions. And those are 1 molar for solutions, 1 atmosphere if any gases are involved, and 25 degrees Celsius. The tables always report the values as reductions. Okay, and that's for good reason. Hopefully it'll become obvious here in a second. So what are they compared to? They're always compared to a standard hydrogen electrode that delivers hydrogen at 1 atmosphere pressure, and it probably has, let's see, if the gas is coming in here, oops, not water. If the gas is coming in here and bubbling out, then there needs to be a conductor. So that's usually platinum, because it's non-reactive, it's inert. And this standard hydrogen electrode, for its reaction side, is given a standard potential of 0 volts. Okay, so everything else is compared to that one. That means when you put them together, you can compare the unknown. You can build your own galvanic cell and use those voltages compared to each other, because they're compared to a 0 hydrogen volt. Okay. Those are standard conditions. If, well, not if, but when one of those half reactions, if you put 2 of those half reactions together, one of them has to be reversed, because you can't have 2 reductions. So one of them has got to be reversed, and you've got to figure out which one needs to be made into an oxidation in order for the reaction to be spontaneous. And by the way, this standard potential in volts is the same for any reaction, as long as these conditions are maintained. 1 molarity, 1 atmosphere, 25 degrees C. It doesn't matter how big the cell is or how small the cell is, it's always that value for standard potential. Now we're going to learn in a little bit how to calculate the actual potential for a cell at different concentrations and different temperatures for that matter. But under these circumstances, standard potential is an intensive property. All right. The other factor is the spontaneous generation of voltage in a galvanic cell always occurs when you are able to calculate an E that's greater than 0. The calculated value of E must be greater than 0 in order for it to be spontaneous. All right, that's going to come in handy later, and we're going to compare that to delta G right? We know delta G Gibbs free energy is identifies a spontaneous reaction if the delta G is negative. So hold that thought. All right, here's part of the table, and notice that everything's in reduction. So the electrons are always on the left-hand side of the arrow. So if we take fluorine, F2, add 2 electrons and get 2 F minuses, then that should produce a positive voltage of 2.87. So when we compare it to the standard hydrogen electrode at 0, then that's the voltage you get for that reaction compared to hydrogen. If we compare it to something else, then we've got to decide which one of these becomes the oxidation step. And the way this table is arranged, if you have 2 half reactions you want to put together, the one above is the cathode. That's the reduction step. So you leave it as is, and its value, its voltage value as is. Then the one below it, you flip it, and you change the sign on the voltage. Then you add them together, and that gives you the overall voltage. So if we have these first two, like fluorine and silver, and let silver be the anode, we flip it, right? Then it becomes a negative 1.99, and add that to 2.87, we get 0.88 volts from the standard potential for those 2 half reactions. And we keep going, and they get smaller and smaller as we go down, compared to hydrogen. There's hydrogen, 0. Now, when we get below hydrogen and the values become negative, in that case, the hydrogen, instead of being oxidized, now we're getting reduction at the hydrogen electrode. And we're getting oxidation at everything else. So these have to be reversed relative to hydrogen, but they're reported as reductions. Okay. All right. So this is what your textbook probably tells you to do. In order to calculate the standard electromotive force, the potential for the whole cell, you take the standard potential for the cathode and subtract the standard potential for the anode. All right. And that works. Yeah, it works fine. If you want to memorize that, that's great. But I like looking at the reactions and saying which one needs to be flipped in order to give me a positive E value. Then I don't have to worry about that equation. All right. Let's see. So here's an example. We have one side, let's see, Fe3 plus. Let's take a closer look at this one. So Fe3 plus to Fe2. Fe3 plus to Fe2 plus. What happens there? As written, we have gained 1 electron per iron. And the copper has lost 2 electrons per copper. So this would be the cathode for reduction, and this would be the anode. So this one would go in the left-hand cell, this one will go in the right-hand cell. All right. So if we want to calculate the standard potential, all right, there are half reactions. This one is 0.77. Okay. And the copper is 0.34 if we write it as a reduction. So in this case, we have 2 electrons here, and here we have 1 electron. All right, so this one would be 0.34 as a reduction if we flipped it. But written this way, we have to change the sign. So now when we put them together, what do we get? 3, 4. 0.43 volts is the voltage for that galvanic cell. The standard potential. Okay, and there we go, and there we go. Now, it's important, not for standard potential, but for later when we calculate the actual voltage, to calculate how many moles of electrons actually moved. Right? So in this case, we would have to double that one, double that one. Oh, no, I'm sorry. Wrong. Double this one, double that one, double that one. So how many electrons would actually move in the balanced equation? It would have 2 moles of electrons moved from that balanced equation. That's important for the future. Okay. Cathode, there's the anode. There's the balanced reaction, and the cell potential is 0.43 volts. Standard potential. Now, since this is an intensive property, the standard potential does not change when we multiply equations by whole number multiples. But we do need to know how many move, because we're going to use an equation later called the Nernst equation to calculate the actual voltage if we know the concentrations of our values, and we calculate, actually, we're going to calculate a Q for the reaction. We also need to know how many electrons move for stoichiometry, because when we have a certain amount of electrons moving, that determines how many moles of reactants and products are consumed and produced in the process. And we'll talk about that later also. All right, now here's a head scratcher that, let's see. I don't know if I want to spend, I guess I should spend time on this one. Strongest to weakest oxidizing agent. So if we want the strongest to weakest, oxidizing agent. Okay. The strongest oxidizing agent is the one that is most readily reduced. The strongest reduced. And this would be the weakest reduced. Okay. So of these, we have Fe, sodium, F minus, sodium plus, and chlorine. So which one is the strongest or the easiest to reduce? Let's put it that way, the easiest to reduce. Most easily reduced. The one with the largest positive standard reduction potential is the easiest one to reduce. It's the most positive, so it reduces the most readily. Right. So here we have the possible reactions, right? Reduction reactions. hold on a second. What did I miss? Oh, okay. There's the iron on the bottom. So we put it in terms of reduction first. And then we say, okay, well, we've got these voltages for reductions, but for instance, that iron at the bottom, that's not the species. The species is Fe, so we would have to flip that one. So that's what we're going to do to each one of these. The most easily reduced. Well, let's start with this one first. So if we flip this one around and we divide by 2, then we need to get a voltage. What is a voltage for this process? Because it's the opposite. Well, no, first we've reduced it to 1 electron. Okay, we're trying to match electrons, right? Right, we don't know what the voltage is there. Sodium is not likely to accept an electron anyway because it's a metal. But this one, the chlorine, has a fairly high positive voltage. Right? And this one, we don't know because it's a metal. So it's going to be toward the back. That one's going to be toward the front. It's going to be the strongest reducer, we think. How about this one? Well, we think it's probably a stronger reducer than sodium. But the sodium ion is sodium ion the better reducer? More easily reduced? Yeah, because it's positive and it attracts an electron. Yeah, that's true. It's a better oxidizing agent because it's more easily reduced. And the fluorine definitely doesn't want an electron, so it's going to be at the bottom of the list. So we tried to intuit the answer to this one, and it's a little iffy. Chlorine is a strong oxidizing agent, but the others don't have standard reduction potentials to compare. However, the remaining fluoride, sodium, and iron should not be easily reduced. Chloride is the strongest. So we're sort of guessing on the last 3. All right. So instead of drawing this picture with anode, cathode, and a circuit and a bridge, which you can do, we need a shorthand version, and that's called line notation. The line notation is written out in the same order as the picture, with the anode on the left and the cathode on the right, but we need some conventions. Okay, we separate the two with a double line. That represents either a salt bridge or a porous disk, either one. Then anywhere we have a phase change, we have a single line. Okay, we'll show you an example in just a second. It's also helpful to add the concentrations, right? Because they may not be necessarily under standard conditions. We could have different concentrations of our in our solutions. So here's an example. If we draw it out in line notation, we have magnesium solid would be one of the electrodes, the anode electrode on this side, and it would be separated from the magnesium that's in solution. Okay, and then on this side, the solutions would be separated by a salt bridge or a porous disk. So we need the solution here in proximity to that solution, separated by that double line. And then this is separated from the electrode, aluminum, in that solution. So the electrons are going to transfer from here to here. Okay? That's an example. There's your anode, there's your cathode. So what if the electrode does not participate in the reaction? If either one of these reactions is occurring completely in solution, right, and the electrode is not participating, then all you need is something to transmit the electrons from one to the other. And we usually use something that's inert, like a nickel chromium wire or platinum wire. They work pretty well. They need to be chemically inert. Even a graphite rod would work in a dry cell battery, like D cell, C's, AA's, AAA's. They all have a graphite rod running right down through the center. That graphite does not participate in the reaction. It just provides a conduit for electrons to move. Okay, so here we have two half-cell reactions, reduction with their reduction potentials, and we need to discover which one's the cathode and which one's the anode. All right. So they're written as reduction potentials now, so we can't add them together yet. One of them has to be an anode and the other one has to be a cathode. So the way I do it is I say, all right, flip one of them. I say, what happens if you flip the first one? Silver plus electron yields silver metal. If you flip that one to make it an anode, an oxide, then you get a -8, negative, and a positive right there. So what do you get when you add those two together? Well, you get 0.03 negative. That's not spontaneous. So we flipped the wrong one. So let's put that one back and let's flip the iron. Now if we flip the iron, we get a 0.03 volts for that galvanic cell. If we make the iron the anode, so the iron would be on the left, silver would be on the right. There we go. And that would be the complete equation there, balanced equation. All right. Let's see, that's nothing new. Okay, in this case, since we have iron 2+ and iron 3+ are participating in the anode reaction, right? The electrode is not involved. So we put a platinum electrode into that solution as a point of reaction and a collector for the electrons. That way they can move from the anode over to the cathode, where the silver electrode does participate in the reaction. And in fact, silver ions are being reduced and silver metal is being plated out on that electrode. Now, one thing that's missing is counter ions, right? You can't have positives in solution on one side and positives on the other, and that will be a buildup of static charge, which doesn't happen. So we need counter ions, right? Iron could be nitrate, right? Or it could be chloride, anything that keeps it soluble. Silver, we wouldn't want the silver side to be chloride. So maybe we don't want chloride on the iron side. because if any of those chlorides migrate to the silver side, they're going to precipitate as silver chloride, and that'll mess up our cell. So nitrate would be better, right? Fe2 NO3 taken twice, and Fe3 would be NO taken 3 times. And then the silver nitrate, so they're always soluble. The line notation would look like this. Notice that the platinum is separated from iron by a line because it's a different phase. But the two irons are only separated by a comma because they're in the same phase. They're both in solution. Whereas on the other side, the silver in aqueous solution is separated from the solid electrode by a line. Now, we're not giving concentrations here because that wasn't part of the problem. Okay. So we need a positive value for E in order to have a spontaneous reaction. It's just repeating things that we've already covered. So I'll just leave it there long enough to be recorded. All right. Okay. If we want to sketch a cell for these two, we need to know what their standard reduction potentials are. And for the silver, reduction potential is, let's see, where is it? Oh, silver would have to be 0.8, right, because it's still positive. And the copper would have to be 0.34. Yeah, we did silver here. There we go. 0.8. Then the copper side would have to be reversed. 0.34 would now be a negative. Add them together and you get 0.46. So what would happen to the potential if you increase the copper concentration? Well, look at the half reaction. Right? On the copper side, we are oxidizing the copper. So copper goes to copper 2 plus 2 electrons. What would happen if we increase the concentration of Cu2 plus in solution? Think of Le Chatelier. If we increase the copper 2 plus ion concentration, it's going to try to force the reaction back to the left. And what would that do? That would reduce the cell potential, right? Because it would work contrary to the oxidation step, right? So overall, we would reduce the cell potential. Now let's try to draw, if we're going to do any work with this electricity that's produced by our chemical reactions, we need to have a sit down with work functions. So we've got the cell potential and we got an expression for work, right? And you remember, let's see, that's not derived though, is it? All right, okay. It just took me a second. If we look at the values for electromotive forces in volts, right? And it's in terms of joules per coulomb. Per coulomb moved, the amount of work that's done is 1 volt. So joules is an expression of work. The problem is when we write an expression for work, it's relative to the system, not the surroundings. And work would be negative if we're doing work on the surroundings as we would be with a battery, right? We're transferring electrons and moving that out of the system and doing work outside. So those values would be positive. But relative to the system, the work would be negative because it's leaving the system. So in order to reconcile that problem for electromotive force, the potential, if it's equal to work over Q, and now we're changing the meaning of Q. Q used to be heat. Now in this context, Q is charge in coulombs, charge, right? If this is going to be positive and this is negative, then to reconcile it, we need to change the sign. Right? So W actually, if we're solving for W, that's equal to negative EQ. Or QE. And the maximum work that can be done, of course, is relative to the maximum voltage that can be expected from that galvanic cell. So this max, let's just write it again. Max equals negative QE max. All right. Now, you see where this is going? What is W max equal to? Let's see. Must be on the next slide. Well, another way of expressing joules, one joule is 1 coulomb volt. Just rearrange the equation. 1 joule is equal to 1 coulomb volt. The actual work that's realized from any of these processes, of course, we learned in the last chapter, is less than the maximum expected. There are so many factors that are involved. One of them, of course, is entropy. But there are other factors that are involved too. Okay. Oh, okay. Before we get to free energy, let's get this conversion factor in here. This is called the Faraday. 1 Faraday is equal to 96,485 coulombs for every mole of electrons that move. There's your conversion factor. So this bridges the gap between the physical and the chemical. So now we're going to talk about free energy. Remember, W max is also equal to the change in free energy. So we can write that over here. Change in free energy is the maximum work that you can get from a process. There it is again. Okay. Now, since Q equals NF, so this would be Q here, and this would be number of moles here. So the charge, we can equate the charge. The 1 Faraday equals coulombs per mole. So if we say Q equals the number of moles times the Faraday, then we can substitute this one into here. So this is negative NF E max equals change in free energy. There we go. Oh, there's a picture of Michael Faraday in his younger days. This guy was absolutely brilliant. He became a member of the Royal Society, which in England was virtually equivalent to a Nobel Prize. And actually, he got into the Royal Society by his discovery of electromagnetism. In short, if you take a coil of wire and you take a magnet and you move that magnet through the coil of wire, it'll cause electrons to move through the wire. That's the whole. That's the theoretical basis for electric motors, generators, alternators, dynamos, all that stuff. So how the modern world functions, actually. So the maximum cell potential is directly related to the free energy difference between the reactants and products in that cell. And it's related by these factors, right? We want to say under standard conditions, that's true. So that just restates the obvious. As long as the cell potential is positive, the cell will run from anode to cathode. And the delta G will be a negative value. So if this is positive, that's positive, that's positive, this would have to be negative based on our convention and the negative fudge factor we introduced. Okay. Now we'll leave that for a second. And introduce another concept. Let's see. I'll leave that one there for now, just in case we need it again. What would be the cell potential if you put two cells together with under standard conditions with exactly the same chemistry going on in each one? The E0 for that galvanic cell would be 0, right? If the concentration in both cells were exactly equal, so let's say they're standard conditions, they're both 1 molar, right? We've got it set up here with a difference in concentration. So the question is, what happens if the concentrations are different, but the chemistries are the same for both of the half cells? Well, now we get into Le Chatelier's principle again. Let's see. Here we go. Le Chatelier says that the lower concentration will increase and the higher concentration will decrease. They're trying to reach equilibrium. All right. So if we wrote this, as a complete equation, then we would have silver in the anode, silver in the anode, with a half reaction for that would be like this, plus an electron. That would be the left-hand side. The right-hand side would be the silver ion in the cathode plus an electron yields silver solid. So that's a solid. This is a solid. This is aqueous solution. This is aqueous. Yeah. This is aqueous solution. Okay. So when you put them together, this one's going to be the higher concentration. This will be the lower concentration. Excuse me. This will be the lower concentration. This will be the higher concentration. So what's going to happen? Well, they're not at equilibrium, right? So what's going to happen is you've got too much of this on that side and not enough on this side. So this is going to be depleted in order to provide this. It's going to move that direction. That's what Le Chatelier said. It's going to move silver from the solid to the ion at the anode. And at the cathode, it's going to go the other direction. It's going to take the silver ions and plate them out on the electrode. Now, how long will this run? It'll run till it reaches equilibrium, right? When the concentration on the cathode side decreases to a point where now the overall reaction is in equilibrium, then it will stop. All right, now we're going to learn how to calculate the actual potential for a galvanic cell based upon their concentrations and actually originally Walter Nernst incorporated concentrations, incorporated temperature into his calculations. He actually got a Nobel Prize for his work on thermodynamics. Here we go. This is the full-blown Nernst equation right there at the upper left-hand corner of that blue box. All right, so it would look like this. The actual cell potential is equal to the standard cell potential, and then we modify it with the gas constant, 8.1345 or 435, remember which, 8.3145, there you go. The temperature in Kelvin, the number of moles of electrons transferred, and the Faraday constant. That accounts for the coulombs. And then you need the natural log of Q. So you have to have the balanced equation, you have to have the actual concentrations, and calculate the Q. If you can do that, then you can put that value in here with the temperature, gas constant, number of moles transferred in the balanced equation, and the Faraday constant, and the standard potential for the cell, and you can calculate the actual potential. Now, that's a lot of work. So what we've done is we've converted the equation so that we can use it under most standard temperature conditions. And that's one of the things we've done. We've also converted the natural log to common log, which is sometimes easier to work with. So when we do that, right, when we convert the temperature from 25 degrees to whatever temperature, right, in K, and then we incorporate the Faraday constant and the gas constant, and we have a conversion factor for natural log to common log, which is 2.3026, then that all combines into this factor. So all we need to know is the number of electrons moved and the Q and the standard potential, and we can calculate E for 25 degrees Celsius. So that's the one that we typically use. I think that's right. 0591. Moles of electrons moved, and then the common log of Q. Okay. And that little box just proves that this 2.3026 is correct. Right? This converts common log, natural log to common log. Right? You don't have to memorize that. I just threw that in there for giggles. Okay, so at 25 degrees C and to equilibrium, what would this equation look like? Well, at equilibrium, that value is K. And at equilibrium, this value is 0. Because at equilibrium, there's no force driving electrons. Right? Everything's settled. Delta G is 0. Not delta G 0, but delta G is 0. And E is also 0. So if we do that, what do we end up with? Well, we end up with, for an expression of standard potential versus K. So we can use standard potential to determine what K is. Or we can find K and determine what the E0 min is. Right? So that's a useful equation. All right. Let's see, equilibrium constant from cell potentials. Okay, so we got this reaction. And we have the standard potentials here. And we're going to find out which one is which, right? If we flip the top one, then we still get a negative number. But if we flip the bottom one, then we get a positive number. So the bottom one, the chromium, is going to be the anode, and the top one's going to be the cathode. But we also need to know how many electrons are transferred, right? So all we need to do is multiply the bottom one by 2. Now we know that 2 moles are transferred. 2 moles of electrons are transferred. Standard voltage is 0.67. And since we're using K, we don't have to calculate any Q value. Well, in fact, we're not given the information to do that anyway. So we plug in our values and solve for K. That's log K, 22.6, and then we solve for K. And we find that the K for this reaction is 4 times 10 to the 22nd power. That's way, way to the right, way to the product side. This is typical for electrochemical reactions. Galvanic cells, they typically have very, very high equilibrium constants. Okay, so what's the difference between E and E0? When is E equal to 0? At equilibrium, when the cell is at equilibrium, otherwise known as a dead battery. When is E0 equal to 0? Aha. For concentration cells. Because for concentration cells, E0 must always be 1 molar for everybody. So if they're both 1 molar, there's no electromotive force driving electrons. All right. So here we have, here we have a concentration cell where the nickel 2+ concentration on the cathode side is 1 molar, and on the anode side is 10 to the -4th molar. So what's the combined equation? Well, we have to be, there's the anode, there's the cathode, there's the cathode, there's the anode. So what we need is, since there's a solid involved here, that's not part of the Q. Remember, K values are not calculated with solids or pure liquids. So all we need is the concentration of the anode nickel and the cathode nickel. And then we can plug them into the equation here. The anode nickel is the low one, right? So 10 to the -4th divided by 1 is 10 to the -4th. And what's the natural log of 10 to the -4? Well, it's 4, right? Well, -4. Yeah, -4. And then times a minus 0.0591 over 2 moles of electrons. And then we get that one. Let's just do that part. Equals 0.0591 negative Is that right? Oh, I left out, excuse me. There we go. Divided by the number of moles, which is 2, and then the common log of 10 to the minus 4th divided by 1. Right? So the log of 10 to the minus 4th is minus 4, right? It's the number that is 10, excuse me. Yeah, that's right. 10 minus 4 times this value, which is a minus. And then E0 is what? E0, where is E0? Oh, E0 is 0. I just told you on the previous slide. E0 is 0 because it's a concentration cell. All right. All right. So if we do that calculation, there, and there. Then we get 0.118. So, and that's typical for concentration cells to have low voltage like that. And in fact, with a difference between 10 to the minus 4th molar and 1 molar, that looks like a lot, but for a concentration cell, it doesn't give you a lot of push. In fact, 118 millivolts. In fact, that's pretty high. And the bigger the difference between the concentrations, the larger the E value. Simply because of this ratio. Okay, we have, let's see, a galvanic cell with 1 molar nickel with an E value of minus 0.23 and a silver electrode at plus 0.80. Which one needs to be flipped? Well, we can't flip the silver because it'll make them both negative. So we have to flip the nickel and make the nickel the anode. If we do that, then we can add them together. Well, there's the line notation. That means the nickel needs to be on the anode side. The silver needs to be on the cathode side. That's true. And there's a sketch. But what's the standard voltage? Here it is. All right. So 0.8 minus a minus 0.23, and you have 1.03 volts for that galvanic cell. All right, so we're going to look at some examples. All right, this is the fun part. Let's see. Oh, yeah, we're going to look at some sample galvanic cells, and then we're going to look, the last topic is going to be electrolysis. All right, this is a sketch of the lead acid battery that's in every gasoline powered car or any diesel powered car. Actually, diesel powered car is probably 24 volt, not 12 volt, but it's the same chemistry. So notice that one of the plates here, the anode, is pure lead. So that means this lead is going to be oxidized to something else, lead 2+ ion. Whereas the cathode is lead 2 oxide. Lead 4 oxide, excuse me, lead 4 oxide. And because each half cell shares the same electrolyte, the same solution, we don't need a barrier between them. It's okay that they mix. So that's a nice thing about lead acid batteries is you don't have to actually physically separate the cells. You just separate the plates. Okay, here's the overall reaction. Right? So sulfuric acid is concentrated. It's very strong in this cell. And in fact, in the old days, lead acid batteries used to have caps in them that had little holes. That was to vent any overcharging, which would produce hydrogen gas. You don't want hydrogen gas building up in your battery, it might explode. But now with technologies, they're able to seal the batteries, and you don't have to worry about that escape of hydrogen. Before, when you had that little hole in there, sometimes the water level, the fluid level in the battery would drop as you converted water into hydrogen and oxygen gas. Then you would have to check your fluid periodically and replenish it. So when most service stations were full service, that was one of the things that the team would do. They'd come out, 3 or 4 guys would come out. One would fill your tank, one would wash your windshield, one would stick his head under your hood and check your battery. And they'd use a little device called a hydrometer. They'd stick it in the battery and pull out some fluid and watch and see if it had a full charge on it. And they check the water level too. And they wouldn't replace it with water though, they would replace it with sulfuric acid. Anyway, so this is the balanced equation that's going on in your battery, and which one is the anode and which one's the cathode. Notice that both the anode and the cathode, the lead and the lead 4 oxide, react and produce lead 2 sulfate. Both of them produce lead 2 sulfate. Where does that lead 2 sulfate go? It's not soluble. It ends up coating the plates. So you get lead 2 sulfate on the plates themselves. And when your alternator runs and recharges the battery, it runs that reaction in reverse and converts the lead sulfate on one of them to lead and on the other one to lead oxide. And that goes on for a number of cycles. You can do that. But eventually, all of the sulfate is not converted, and it tends to coat the plates and prevents them from having access to the fluid, the electrolyte. And when that happens, when it gets so far that you cannot recharge your battery, well, your battery's dead, of course, but your battery is said to be sulfated out. And those were evil words. When you heard somebody say your battery is sulfated out, that was death. You had to get a new battery. All right. So here's a dry cell, typical dry cell battery, and there's a reaction going on here, and the reaction is occurring right there on that cathode, and that's where the electrons are coming in. They're being delivered through that graphite rod into the solution, into the paste actually, for the cathodic reaction, and then the anodic reaction is occurring in this shell made of zinc. Okay. All right, here's another type. We don't use these types anymore because they got mercury in them. But the battery is constructed in such a way as the container itself is one of the electrodes, is part of the reaction. This one is a fuel cell. It is a galvanic cell of sorts, but it can run continuously as long as you have a ready supply, in this case, of hydrogen gas and oxygen gas. They diffuse through the membranes, these porous carbon electrodes, and when they combine, the anode reaction occurs here on the hydrogen side, and electrodes are then dumped into this electrode, and they go through an external circuit, and they show up on this side, and that's where they reduce the oxygen. And the product is water. That's it. That's all you get out of this is water. So this would be perfect for the environmentalists if you had practical fuel cells to run all our vehicles. Then all you would need is a cheap, ready source of energy to split water. Right? You would electrolyze water into hydrogen gas and oxygen gas. Let's see, 2 and 2. So you put energy in, because this is not spontaneous, and you split the water, and then you would have, you could put that in your vehicle. Actually, all you need is hydrogen. You get oxygen from the air, and then run your vehicle on this galvanic cell, this fuel cell. There are several problems with it. In other words, how do you store hydrogen safely in a vehicle so that if you crash it, you don't go up in a big ball of flame like the space shuttle did? So that's one problem. You don't want to store a tank in your car that has to be held under 3,200 pounds of pressure. You want it in some material, and they're working on it, material that is just above atmospheric pressure, and that will deliver hydrogen reliably at near atmospheric pressure. And then operating temperature. These fuel cells originally operated at very high temperatures. They were dangerous, and they had to be well insulated. But they were an efficient form of producing electricity. So that's why they put them on spacecraft, right? And the Apollo 13, remember, had that bad accident. They blew up one of their oxygen tanks. That oxygen was used not just for the astronauts to breathe, but it was also used to run their fuel cells. So their spacecraft was dying. It had no power. They had to shut everything down and live off of the oxygen they had left until they could get back. But these fuel cells operate at very high temperature, and they're very expensive. Now, we brought the temperature down through research over the years, but it's still not practical. Okay, now what do we mean by corrosion? Corrosion is a term that means the conversion of pure metal into a more natural state, which would mean, what is that metal in the ore? Metal ores are usually combinations, they're compounds. So iron typically is iron oxide, Fe2O3, or some variant of that, right? So when iron rusts, it's corroding and going back to, spontaneously going back to Fe2O3. How do we prevent that corrosion? In other words, the metal becomes the anode. It is being oxidized. It's losing electrons. This is what happens on the surface of iron when you get a water droplet there. It sets up a galvanic cell right there in that little drop, right? This is the anodic section. This is the cathodic section. Cathodic section out here. So how do you protect yourself from these types of corrosions? Well, there are several ways you can do it, right? If you can keep the oxygen away from the metal and the water away from the metal, then you can stop it from rusting. And there are several ways to do it, right? You can paint it, right? Which you have to periodically do again. You can plate it in a metal that is more active and will corrode faster than the metal underneath it. So if you've ever seen, if your grandparents still have these buckets laying around, these galvanized buckets, they just take a steel bucket and they dip it in molten zinc. Pull it out, hang it on a hook, and let the zinc solidify. And that's your galvanized bucket. And it will not rust, because there's a very thick coat of zinc on it. And what does that zinc do in the presence of oxygen? Well, it goes to zinc oxide. All right. Let's see. C2. Is that right? Need 2 here. Yeah, 2 here. And it corrodes much faster and more readily than the iron underneath, the steel underneath, and it creates an oxide layer on the surface. So it prevents any oxygen from getting through even to the rest of the zinc. Another way, you can alloy your metal with a metal that is more reactive than the metal you want to retain uncorroded. So that's the idea behind stainless steel. Stainless steel originally, not now, but originally was 35% by mass chromium. Chromium is a very active metal. And what happens is, once it's in the alloy, the chromium itself will oxidize and form a thin layer right on the surface of the metal and exclude any oxygen from getting through. And if any of it does, it immediately reacts with the chromium and not the iron. So that's stainless steel. Another way is cathodic protection. You can separate the active metal from the iron as long as you've got a conductor connecting them, delivering electrons through that wire to the iron. So this buried pipe becomes the cathode, and this magnesium becomes the anode. The magnesium corrodes underground, and as it does, it delivers electrons through that wire to the pipe and keeps the pipe from corroding. They use this on ships too. They call it cathodic protection. You'll see them, sometimes they'll have a band of zinc all the way around the ship. And other times you'll have these ingots of zinc stamped or riveted onto the surface of the ship periodically. And those things corrode and deliver electrons, as the anode delivers electrons to the steel hull of the ship and keep it from corroding. All right. And in your water tank and all your pipes are protected because there's an anode in your water tank made out of aluminum. And the aluminum corrodes instead of corroding your pipes, corroding your valves. Okay. Now for electrolysis. This is our last topic. Think of electrolysis if the galvanic cell is spontaneous in the direction from the anode to the cathode. Then electrolysis is not spontaneous in the other direction, but we can drive it that way. All we have to do is apply an external voltage greater than the voltage of the spontaneous cell. So if the cell has a 1 volt potential from the anode to the cathode, all we need to do is apply a reverse voltage greater than 1 volt, and it will drive the reaction backwards. And when that happens, if you do that, now which is the anode, which is the cathode? It's still the anode is the site of oxidation. So now the cathode in the electrolytic cell becomes the anode, and the cathode now is where the anode was. you effectively drive the reaction backwards. I put this one on the board a minute ago. This also happens in your lead acid battery. When the alternator is running, it recharges the battery by turning it into an electrolytic cell and driving the reactions backward and reconstituting the lead plate and the lead oxide plates. All right. So if we need to do calculations for electrolysis, we need to know several things. Sometimes we need to know, most times we need to know the balanced equation for the galvanic cell, because we're going to run it in reverse. And we have to know how many electrons, how many moles of electrons are going in reverse to drive the reaction backwards and produce usually a metal. Not always, but for our example, would be a metal. So, and once we know that, then the solution to the problem becomes a unit conversion problem. All right, so here's an approach, right? If you're going to drive the reaction backwards, you need to know the current. In other words, how much charge is being delivered over a certain period of time. That's how many coulombs is moving. Then we convert the coulombs to moles of electrons, and then through our balanced equation, we convert the moles of electrons to the moles of the metal being plated out on the cathode. And then if we need to know it, we can convert the moles of that metal into mass. Okay. And there's our conversion factor, moles of electrons to coulombs. We definitely need that. So here's a problem. Say we have an unknown metal, and it took 52.8 seconds for a current of 2 amps to plate out 0.0719 grams of the metal from a solution containing Mn, the metal, and 3 nitrates for each of the metal, for the metal. So we know, excuse me, not manganese, the metal and the nitrate, right? Well, it's going to produce that and this. Right? So how many moles of electrons would be required to produce the solid metal from the ion? Well, it would be this. Force of habit. It would be this plus 3 moles of electrons yields one of these. Okay? So we know that the N equals 3 moles. 3 moles for every mole of metal. Okay? We also know that it took 52.8 seconds to occur. So how much charge is delivered? Well, 1 amp is 1 coulomb per second. So we have 2 amps, coulombs per second. Okay, now we know how many coulombs are required, but we need to know how many moles of electrons. So we got to convert coulombs to moles of electrons. So what's the magic number? 96,485. Coulombs. So we cancel the seconds, we cancel the coulombs. Now we have moles of electrons. Okay. So how many moles of electrons per mole of metal? Well, 3. 3 moles of electrons for every mole of metal. Okay. Now, I did skip one thing. We want to identify the metal, right? We don't know how many protons it has, but we could determine possibly the molar mass. So the molar mass of this metal would be the mass per mole of the metal. This is going to tell us how many moles of metal there are, right? So that will fill this, and we know that the mass is 0.0719 grams. So we just need to solve that one for the moles of the metal. Let's see, 52.8 times 2 divided by 96,485 and divided by 3. So this is 3.65. 3.65 times 10 to the minus 4 moles. Okay, so the molecular weight is equal to what? Let's see, 0.0719. 0.0719. I get 197 grams per mole. So now we go to our periodic table and look for 197. Let me see, I got to get a little closer. That looks like the closest one to that is gold. All right, there's the calculation. And we determine that the metal is gold. All right. Oh, one more thing. If we have a mixture of ions in solution, since the process of electrolysis is similar, except in reverse, of the galvanic cell, then it's an intensive property. So all we really need to know is if we want to determine which one of these ions plates out first, what's the order? Then all we need to know is their standard potential. So the metals are going to form on the cathode. Let's see, we put that in there already. The more positive the standard reduction potential, because that's what we're doing. We're reducing these ions into the metal. So the higher the positive value, those are the ones that are going to come out first. Let's see. The more positive the standard reduction potential, right, as the voltage is increased. There we go. So, oh, these are in order. Okay. So the first one that's going to come out is copper. Second one that's going to come out is lead. Tin comes next, nickel comes next, and zinc comes next. If you have a mixture of these metals and you want to purify them, right? Say you have you've purified copper to 95%, but it's got all these bunch of these other metals in there with it, right? All you have to do is run this cell in reverse at 0.16 volt or less. Well, actually 0.16, but not 0.13, negative 0.13. So you can bring the copper out first and leave all the rest of them behind. And that will give you 99.99% pure copper. And that's the way they do it. They electrolyze copper in order to produce, especially copper for electric wires, for electrical wiring, because it needs to be very pure. And for communication wiring as well. Okay, I think this is the last one. So where do we use electrolytic processes? Well, definitely for the production of aluminum. Right, I'm going to describe that to you in a minute. Purification of other metals, yes, we do use it for that. We use it for plating. Right, cars used to have chrome-plated steel bumpers. Right, if you go to antique car shows, you'll find quite a few of these cars have chrome-plated bumpers. Right? Chrome plating was a way not just to make them look pretty, but to protect the steel underneath from rusting. and they immersed the steel bumper in a big vat of chromium ions, and then they ran a charge through the bumper, direct current, and caused the bumper to become the cathode and played out chromium on that steel. Actually, it's a little more complicated than that, but that's another topic. Essentially, it's an electrolytic process. We can also take pure sodium chloride salt, and we can run the current through it and produce sodium metal and chlorine gas. Right? So you take the sodium and you put it in water and you make sodium hydroxide. Right? And you take the chlorine and you bubble it through that sodium chloride solution and you make sodium hypochlorite, which is bleach. It's used for a bunch of other stuff than that, but that's just one good example. All right, this process for producing molten aluminum was perfected by two people, a young man by the name of Hall and a Frenchman by the name of Héroult. And they both applied for patents pretty close to each other in the same year. But Héroult got his in Paris in France, and Hall got his in the United States. And Héroult tried to impose his patent on the US market. So Hall took him to court and determined that Hall had filed for his patent before Héroult did in this country. So Hall kept his patent and profited from it. But what he does is he takes aluminum oxide, which is the purified form of the ore, the aluminum ore called bauxite. And bauxite can be found usually in the tropics. And some preliminary processing is done before it's shipped back to factories for electrolysis. And aluminum oxide, then you melt it. Right? Why do we have to melt it? Because ionic solids are insulators. Their ions cannot move and they're not accessible. So we have to melt it. The problem is that aluminum oxide melts at over 2,000 degrees Celsius. And that was too much. So what Hall discovered was if he combined aluminum oxide, about 10%, and the rest of it was cryolite, which is aluminum sodium fluoride. Then he could reduce the melting point to less than 1,000 degrees, which is quite an improvement. And then electrolyze it. Right? Just run a current through it to drive the reaction backwards from aluminum oxide to aluminum and some other products. But aluminum then would settle to the bottom of the tank. You just knock the plug off of it, and out comes pure aluminum. Before this, aluminum was extremely expensive because it was produced by purely chemical means, not electrolytic means. In fact, Louis XIV, right, the Sun King of France, would serve meals in his state dinners using aluminum silverware because it was more expensive than gold. Let me see. Did I have something else I wanted to say here? Occasionally, you'd have to stop the process and replace these graphite rods and reline the tank with graphite because they would be eroded over time. You can electroplate your silverware. In fact, if you want to do some spontaneous reactions, all you need is a baking dish and aluminum foil and salt water and a corroded silver utensil. Just lay it in here on that aluminum, and it will spontaneously convert the silver corrosion into silver metal without polishing. That's really a galvanic process, not an electrolytic process, because that's spontaneous. But you can electroplate. And here's your molten sodium chloride making chlorine gas and sodium metal. All right, that's it for the introduction of the material.